Okay, so think we're underway here. Good morning. I'm going to go ahead and stop sharing for just a second to make sure. Yeah, it looks like we are recording. So good morning. Hope everybody is doing well. Wanted to jump right into our work for today, which is a little bit tough. It's some tricky stuff. I'm looking for my pen, which I seem to have misplaced. Oh, there we go. So we're talking about what's called calorimetry. So we've been talking about heat and exothermic and endothermic reactions, and we talk about heat being measured in, energy, heat, they're one and the same thing, being measured in joules. Now, we have to find a way to measure heat, and we do know thermometers measure temperature, but temperature is not heat, all right? So we need to make a connection between those things today. So how do we measure the energy in bonds? We look at how much energy is released, all right, or absorbed, and we do some calculations. And that's what we do in order to calculate this heat, this delta H term that we were looking at in those problems a day or two ago. And what we're going to use to help us figure this out is what's called a calorimeter. And I'm going to see if I can get, there's a picture of it here at the bottom of the notes. And it is literally a very well insulated container, right? And so the actual reaction takes place in this inner chamber. And what we do is we then have this inner chamber, which is submerged in water. And we measure the temperature change of the water. And we figure that if this thing is exothermic, it's going to give off energy. And so if you think about that, that's going to then change the temperature of this surrounding water. And if it's giving off energy, the water's temperature will go up. Conversely, if this thing is absorbing energy, it's going to be endothermic. It's going to be taking energy from the water, which would make the water colder. And the reason that we use water is because it's got this huge, what we call specific heat. And we're not going to get too deep into this because we're just not. And but what this is, this specific heat of water is telling me that for every gram of water that I have, it's going to require 4.184 joules of energy to change that 1 gram of water by 1 degree Celsius in temperature. So we like using water in our calorimeters because water is easy to use and it has a relatively high specific heat. So even if there's a lot of heat associated with the reaction going on in here, right, it takes a lot of heat to change the temperature of water. So the calorimeter, let's see here. I think the rest of this is pretty self-explanatory. Down here at the very bottom, we say that, hey, and this is what I was saying a moment ago, if the reaction gives off heat, all right, then that's going to be equal to the amount of heat gained by the calorimeter. All right, that's why these things are oppositely signed. If this thing, the reaction is absorbing heat, then that's going to be equal to the amount of heat that is lost by the calorimeter. So they're the same number, but they have opposite signs because one is gaining and the other thing is losing. All right, so big stuff here, guys. And these are problems that are challenging for students. So we're gonna do some problem solving here. So remember that when we talk about heat, the unit is the joule. And this guy is a biggie, all right? This is the formula. If you ever want to know how much change in heat, how much heat is associated with a change in temperature of a substance, we're going to use this. Q equals MCT, all right? I like to call it MCAT because it looks like an A there, but and so what we need to understand, what are these symbols? Q represents the amount of heat, the amount of energy in joules, right? M is the mass of water, all right, used in the calorimeter, all right? Now, more generally, if we're talking about just any substance, we're talking about heating up a bar of aluminum, all right? We'd want to know the mass of the aluminum. C is the specific heat of the material. Now, if we're talking about calorimetry, if we're doing these problems where we are looking at how much heat is associated with a reaction, we're always going to be using water, okay? And so C, all right, for lots and lots of problems will be 4.184 joules per gram degree Celsius, all right? Now, if for some reason we're doing this in another unit, We could be talking about the amount of energy in calories, because calories and joules are both units of energy. But I'd say for most of the problems that we'll do, C, if we're talking about water, we're talking about a mass of water, we're going to use a C of 4.184. If we're talking about the amount of heat associated with a bar of aluminum, we would have a different specific heat. And if you think about it, metals are really easy to change the temperature of. All right, that's why they feel cold when you touch them. When you grab some metal, all right, the metal is at room temperature, and room temperature is usually like 72 degrees, and body temperature is at 98. That's a difference of like 26 degrees Fahrenheit. But the metal that you touch usually comes up to your temperature pretty quickly because its specific heats for metals are typically very small. It does not take a lot of heat to change the temperature of a metal. And so eventually, pretty quickly, your hand brings the metal up to temperature because your body is always giving off heat. You're a furnace. All right, so, and then the last part is delta T. That is the change in temperature of the material, all right? So Q equals MC delta T, all right? And big understanding here. So the heat lost or gained from chemical bonds in a reaction can be calculated by looking at the heat gained or lost by water in a calorimeter. I'm gonna cough here, see if I can save you that sound. Okay, sorry about that. And now let's go ahead and look at this. So we're gonna say, let's take 1 gram of ammonium nitrate, the N4NHO3, all right? And we go ahead and dissolve it into 50 grams of water. All right, and the process of dissolving it, of literally taking this solid ammonium nitrate and turning it into ions, dissolving in water, making it aqueous, all right, causes the temperature of the water to change from 25 degrees to 23.32. So if you put this in the container and you stirred it up, you would see the temperature drop. So if we saw a temperature drop, all right, we would know that, okay, it's getting colder, so it's absorbing energy from the environment, from the water. And if it's absorbing energy, if this process absorbs energy, that is called an endothermic reaction. So we're going to end up calculating this delta H here using this Q equals MC delta T, all right? So first off, there's a lot of things to keep straight in these problems. So you focus on what we know. Well, what do we know? We know we have 50 grams of water. So we know the mass of water. We also know from the notes that we just took or looked at, the specific heat of water, the amount of energy required to change 1 gram of water by 1 degree Celsius is 4.18. So we know the mass, we know the specific heat, C. And then we ask ourselves, well, what was the change in temperature? And change in temperature, you have to be careful with this, is always going to be final temperature minus initial temperature, all right? So you know that your final temperature was 23.32, you know that you started out at 25, and the way I like to kind of remember it is double check your sign. If it dropped temperature, it should be a negative. If it gained temperature, it should be a positive. So at this point, I go ahead and look at my Q equals MC delta T formula. And so this is going to tell me that the amount of heat associated with this process, all right, so the water itself, the water in the calorimeter, right, gave up 351 joules of energy, all right? Well, what that means is, because what we said was that the change in heat of the calorimeter is equal to the opposite of the change in heat for the reaction that we're studying. So all we did was we said, oh, flip the sign, because if the water is giving up heat, that's because the reaction absorbed heat, and that's an endothermic reaction. So we got a cough here. Excuse me. This is how we do sort of a relatively basic beginning calorimetry type of problem. Not easy stuff, guys. You definitely have to keep your wits about you. And now it's just going to get really complicated. I get some more water. Okay. Now, at this point, I think what I'm going to do is pause this video and make a part two, just so that the videos don't get too long. Um, so I'm going to stop, and I will see you guys in just a moment here for part two of our calorimetry notes, and see you in a minute.